Imagine, you've made an AI system that predicts queuing times at the airport. Its predictions are used to inform passengers about how long they have to wait at the security checkpoint and the border control station. The system is also used by the border control agents and security staff to optimize their personnel allocation. For example, when they see that the queuing time is predicted to rise to 30 minutes at a certain security checkpoint, they may choose to transfer a staff member there to try to prevent that. As a developer, you've been getting questions from the border control agents. They've noticed that the predictions for long queues sometimes seem to be unreasonable at first sight. On a calm day with very few flights leaving, the waiting times could sometimes be inexplicably long. There are also days that are usually busy, where the AI system predicts a drop in queuing times for a while. How would you explain the cause of these strange predictions? Machine learning models typically take in data from many different sources to make their predictions. Many modern machine learning models also have complex mathematical structures with a large number of parameters, making it difficult to reason about them. In this sense, models can be seen as black boxes. You can see that they work, but it's hard to determine how, and even harder to explain why they do what they do. There are, however, some models that are easier to understand and techniques that can make opaque models more transparent. Let's start with an example of a model that's easier to understand, a decision tree. You can see this as a number of branching logic statements. If this model makes a prediction, it's easy to trace back the decisions it took and give this as an explanation. You may have noticed that this can raise more questions. Why that specific set of rules and not other rules? What if one of these variables was a little bit different? That brings us to another way of explaining predictions. The rules in our decision tree model are based on a number of training examples. It might be interesting for the users of a model to see what kind of examples contributed to the result they saw, as a kind of explanation by example. This would, however, require us to keep at least part of the training data and have a way of associating a new prediction with training examples, which doesn't always work. For those cases, there are some more advanced methods we can use. For example, in neural network-based models for computer vision, we may be able to show which parts of an image contributed the most to the final result. Let's get back to the airport queuing time case and try to piece together a way of explaining to the border control agents why these strange but very relevant spikes sometimes appear in the predictions. The model we use looks at many different variables, like the countries our passengers are flying to. If most passengers are flying to an EU country, the agents will have little to do. But if a large number of passengers are flying to a country that requires extra checks, the agents will take more time per passenger, resulting in longer queues. The model was able to learn this from the examples it got, and we can use an analysis technique to highlight that the destination country variable was the one that contributed to most of these extreme situations. We hope we've been able to illustrate that explainability is an important topic for AI and machine learning projects. Also, that machine learning models aren't incomprehensible black boxes. In the end, everything depends on the type of explanation the client needs and which tools we can use to give it to them.